For centuries, humanity has conceptualized the arena of reality, space and time, as a smooth, featureless, and continuous backdrop. From the absolute stage of Newtonian mechanics to the curving, woven fabric of Einstein's general relativity, spacetime has been the silent canvas upon which the dramatic events of the cosmos unfold. However, a profound paradigm shift is currently underway at the absolute bleeding edge of theoretical and experimental quantum physics. Imagine a universe where the foundational structure of reality is not a smooth continuum, but a pixelated, ever-shifting, mathematically precise mosaic. Even more mind-bending, imagine that this mosaic never repeats itself, yet is completely, flawlessly ordered. Welcome to G-Fun Facts Online. Today, we are exploring the strange, beautiful, and revolutionary world of spacetime quasicrystals. Driven by recent experimental breakthroughs in quantum mechanics and radical new theoretical formulations of quantum gravity, scientists have begun to demonstrate that the universe might operate as an infinitely complex, aperiodic crystal extending through both space and time. Through the creation of time quasicrystals inside laboratory diamonds to the mathematical discovery of Lorentzian spacetime quasicrystals that bridge general relativity and quantum mechanics, we are looking at an entirely new blueprint for how reality is put together. To truly understand a spacetime quasicrystal, we must first grasp the concept of a spatial quasicrystal, a structure that completely broke the rules of traditional chemistry and earned Dan Shechtman the 2011 Nobel Prize in Chemistry. For over a century, crystallography was built on a very strict rule, which is that a crystal is defined by its periodicity. If you take a basic geometric unit like a cube or a hexagon and stack it infinitely in all directions, you get a regular crystal, much like a bathroom floor tiled perfectly with squares. Because of the rigid rules of three-dimensional geometry, true crystals can only possess certain rotational symmetries, specifically twofold, threefold, fourfold, and sixfold symmetries. For a long time, a fivefold or pentagonal symmetry was deemed mathematically impossible to tile seamlessly without leaving empty gaps. Quasicrystals shattered this dogma entirely. They are highly ordered structures that never repeat themselves exactly. If you were to slide a quasicrystal over a copy of itself, it would never perfectly align in the way a standard periodic crystal does. Yet, they follow strict mathematical rules, often governed by irrational numbers like the golden ratio. The most famous mathematical analogy is the Penrose tiling, conceived by the brilliant physicist Roger Penrose, which uses just two shapes, known as kites and darts, to tile a two-dimensional plane infinitely without ever repeating the overarching pattern. But how do these seemingly magical, non-repeating structures actually form in nature? The mathematical secret to generating a quasicrystal is a fascinating technique called the cut and project method. Imagine a perfectly periodic regular grid of points, but existing in a higher dimensional space, say 5 or 6 dimensions. If you slice a lower dimensional plane like a 2-dimensional or 3-dimensional sheet through this higher dimensional grid at a very specific irrational angle, the points that fall near the slice project onto it as a quasicrystal. Because the slope of the slice cannot be expressed as a simple fraction, it never perfectly intersects the repeating nodes of the higher dimension. The resulting lower dimensional shadow is completely ordered by the geometry of the higher dimension, yet infinitely aperiodic. Until very recently, this phenomenon was restricted to physical materials in 3-dimensional space, found only in rare meteorites, the debris of atomic bomb tests, and synthetic laboratory alloys. But physics has recently forced this geometric oddity into the 4th dimension, time itself. The journey from space to spacetime began with the mind-bending concept of a time crystal. Originally hypothesized in 2012 by Nobel laureate Frank Wilczek, a time crystal is a phase of matter where particles undergo continuous, repeating oscillations in time without consuming or losing any energy. They essentially exhibit spontaneous symmetry, breaking in the temporal dimension. They are the closest thing nature allows to a perpetual motion machine, locked in a quantum ground state that endlessly ticks without a power source. But in March 2025, physicists at Washington University in St. Louis, along with collaborators at MIT and Harvard, unveiled a monumental upgrade, the world's first true-time quasicrystal. To engineer this entirely new phase of matter, researchers began with a millimeter-sized diamond. Using powerful beams of nitrogen, they bombarded the diamond to knock carbon atoms out of their lattice, creating what are known as nitrogen vacancy centers. These are empty atomic chambers into which electrons flow and immediately begin interacting via the strange laws of quantum mechanics. The scientists then bombarded these quantum systems with highly calibrated microwave laser pulses to trigger a rhythmic temporal dance. In a standard time crystal, the electrons would oscillate back and forth in a predictable, periodic rhythm, exactly like a metronome. But in this new time quasicrystal, the particles vibrated in a highly structured but entirely non-repeating pattern. Different dimensions of the system vibrated at distinct, overlapping frequencies, creating a complex temporal structure that is more akin to a rich, evolving musical chord than a single, repeating note. The system was highly ordered, yet fundamentally aperiodic. The implications of this 2025 discovery are absolutely staggering for the future of quantum technology. Standard time crystals are notoriously fragile, breaking down rapidly under environmental interference. Time quasicrystals, however, exhibit unique, robust properties. Because they do not rely on a single resonant frequency, they are incredibly sensitive to multiple frequencies at once. This paves the way for ultra-precise quantum sensors, highly advanced metrology, and a new generation of quantum memory that functions analogously to an undegradable quantum RAM. Imagine a quantum sensor that never requires recalibration, or a clock that measures the very fabric of reality without ever losing a fraction of a millisecond. While experimentalists were busy conjuring quasicrystals of time and diamond defects, theoretical physicists were asking an even deeper, more profound question. What if the ultimate fabric of reality, the four-dimensional spacetime of the universe itself, is actually a quasicrystal? For decades, theoretical physics has been haunted by the glaring incompatibility between general relativity, which is the physics of the macroscopic universe, gravity, and smooth spacetime, and quantum mechanics, which is the physics of the microscopic, characterized by discrete, pixelated packets of energy and fields. Efforts to create a unified theory of quantum gravity, such as loop quantum gravity or emergence theory, often propose that at the smallest conceivable scale, known as the Planck length, roughly 1.6 times 10 to the negative 35 meters, spacetime is not smooth, but discrete or granular. The fundamental problem with a discrete, pixelated spacetime is that it seems to violently violate Lorentz symmetry. Lorentz symmetry is the ironclad rule of Einstein's special relativity, stating that the laws of physics must remain perfectly invariant regardless of an observer's velocity. If spacetime were an ordinary, repeating grid or crystal, an observer moving at 99% the speed of light would experience length contraction and see the grid deformed, meaning the universe would look fundamentally different depending on how fast you were moving. This is strictly forbidden by relativity. In January 2026, physicists Latham Boyle and Sotirios Migdalis published a breathtaking paper that solved this mathematical impossibility, formally introducing the foundation of Lorentzian spacetime quasicrystals. They demonstrated that by generalizing self-similar quasicrystals from standard flat Euclidean space to the curved, four-dimensional Minkowski spacetime of relativity, one could construct an inherently discrete, pixelated universe that strictly preserves Lorentz symmetry. The breakthrough relied on that familiar cut-and-project mathematical method we discussed earlier, but scaled up to staggering cosmological proportions. Boyle and Migdalis showed that if you take a highly symmetric higher-dimensional space, such as an 8-dimensional or even 10-dimensional Lorentzian lattice, like the even self-dual lattice closely associated with string theory, and slice a 4-dimensional plane through it at an irrational angle, the resulting projection is a spacetime quasicrystal. Because of the irrational angle of projection, the resulting structure possesses infinite, non-crystallographic orientational symmetry. In simpler terms, a spacetime quasicrystal scales seamlessly. It possesses global scale invariance and self-duality. An ant sitting completely stationary and an ant rocketing through the void on a ship at near light speed would both perceive the exact same overarching geometric order. Relativity is perfectly preserved, but spacetime is allowed to be fundamentally discrete, granular, and pixelated. So what does a universe built on a spacetime quasicrystal actually look like? And what deep mysteries of physics does it resolve? The structure dictates a reality governed not by cycles or repeating loops, but by a steady, unfolding internal logic. Picture an infinitely long corridor where small lights flash. The flashes never form a simple repeating rhythm, yet they never devolve into pure randomness. The spacing is mathematically controlled, predictable to those who know the higher dimensional rule, yet eternally novel. This is the precise flavor of a reality underpinned by spacetime quasicrystals. Most critically, this framework provides a highly elegant geometric solution to one of the most stubborn mysteries in modern physics, the massive, unexplained hierarchical gaps between fundamental energy scales. In standard physics, there is a massive, confusing void between the Planck scale, the electroweak scale where electromagnetism and the weak nuclear force merge, and the vacuum energy scale driving the universe's expansion. In a standard continuous universe, these vast numeric discrepancies have no organic explanation and require messy mathematical fine-tuning. But within the framework of a spacetime quasicrystal generated from a 10-dimensional space, the built-in scale factors of the geometric projection naturally mirror these exact energy gaps. The seesaw relationship between the Planck scale, the vacuum energy, and the electroweak scale emerges organically as a fundamental mathematical feature of the quasicrystal's geometry. The universe is the way it is because it is the mathematically inevitable shadow of a higher dimensional order. The paradigm shift, triggered by spacetime quasicrystals, extends even into the grandest macroscopic mysteries of cosmology, including dark matter and the expansion of the universe. In standard condensed matter physics, crystals and quasicrystals feature quasi-particles, which are quantized modes of vibrations. The most common are phonons, which represent waves of acoustic energy moving through the lattice. However, quasicrystals have an additional, highly unique quasi-particle, known as a phason. Because a quasicrystal lacks translational symmetry, any attempt to deform or rearrange the internal tiling of the quasicrystal requires the atomic flips of phasons. Recent cosmological models published between 2024 and 2025 have proposed a heuristic framework modeling the entire expanding universe as a dynamically growing quasicrystal. Rather than the universe expanding like a balloon stretching smoothly, spacetime is conceptualized as a tiling space that geometrically scales and grows through discrete, quantum-level topological additions. In this framework, the intrinsic growth dynamics of the quasicrystal naturally give rise to the large-scale expansion we observe, potentially resolving the notorious Hubble tension, which is the frustrating discrepancy in measurements regarding exactly how fast the universe is expanding. Furthermore, the mathematical existence of spacetime phonons and phasons interacting with this expanding geometry provides an astonishing new candidate for dark matter. Just as weakly interacting massive particles are theorized to exist like ghosts among ordinary matter, phonons and phasons undulating through the spacetime quasicrystal could possess immense gravitational influence without interacting via electromagnetism. The phantom dark matter holding our galaxies together might not be an elusive new particle at all, but rather the acoustic and topological vibrations of the spacetime quasicrystal lattice itself. The revelation of spacetime quasicrystals is currently acting as a great unifier across disparate scientific disciplines. It binds the elegant, irrational number mathematics of Penrose tilings to the Lorentz invariant symmetries of special relativity and merges them flawlessly with string theory, Lie groups, and quantum sensing. We are rapidly moving away from the old paradigm of reality as an empty box filled with wandering particles. Instead, fundamental particles, the forces of nature, and the very fabric of the cosmos are not things existing inside space. They are localized geometric deformations, topological twists, and vibrational nodes of a fundamental quasicrystalline network. The practical offshoots of this paradigm shift are already taking root in laboratories around the world. From Washington University to MIT, experimentalists are harnessing the localized temporal vibrations of time quasicrystals to forge quantum devices capable of storing information flawlessly across long periods. Meanwhile, theoretical models continue to probe whether the geometric code of the universe could eventually be manipulated. While strictly in the realm of speculative physics today, if fundamental reality is truly a projected mathematical code of localized deformations, understanding the syntax of this quasicrystal could fundamentally redefine our limits regarding space, time, and motion. From the atomic debris of nuclear tests, to the brilliant heart of a microwave lasered diamond, and ultimately to the mathematical modeling of the entire cosmos itself, the quasicrystal has proved to be nature's most magnificent paradox. It is an architecture of chaos and absolute order, perfectly entwined. If the universe truly is a space-time quasicrystal, it means we live in a cosmos devoid of monotonous repetition, uniquely unfolding at every coordinate and every quantum tick, forever projecting an infinite, unpredictable, and beautiful mathematical truth. Thank you for joining us today on G Fun Facts Online, where we continue to explore the absolute bleeding edge of the universe.